Welcome everyone to today's technical lecture. AusYGN is most happy to have the chance to organise this event and hopefully many more in the coming months. These lectures are driven from AusYGN's goal of promoting the transfer of knowledge between young nuclear professionals. And I'm sure all of us will gain much understanding about the global nuclear context in which we work within from the talk today. So with that, I'd like to introduce our speaker, Dr. Mark Ho. He will be speaking on the current and future developments in nuclear power. Mark is a researcher at ANSTO, working with the nuclear analysis section on the development of computational fluid dynamics, fuel-cooled boiling models, fluid experiments, as well as being involved in the review of safety analysis documentation for the open reactor. He has a doctorate in mechanical engineering from the University of New South Wales in computational fluid dynamics and has interests in the economics, science and technology of nuclear power. He's also the president of the Australian Nuclear Association, which promotes the knowledge and practice of peaceful, safe and effective use of nuclear science and technology, and provides a forum for the presentation, exchange and dissemination of information in the field of nuclear science and technology. Today's lecture will include a short talk and then plenty of time for questions and discussion. So please save all your questions for the end. Let's show a big welcome for Mark now.
Okay. Thanks very much, Julian. And I'm very honored to be here for the inaugural technical lecture for AusYGN. Okay, so I just like to start with this slide because this slide, even though most people don't think of Sydney as being a hub of nuclear expertise, it actually is. Of course, everything kind of somewhat gravitates around ANSTO, which is the custodian of the Opal Research Reactor. Surrounding ANSTO, though, are APANSA, the regulator, UNSW, which has a nuclear engineering master's running, as well as the nuclear engineering panel over at Engineers Australia, as well as also, of course, our own Australian Nuclear Association, which is a professional body of nuclear engineers and scientists. Now, the very first slide I often like to make is a little bit of an explanation about ionizing radiation, because most people don't really have a feel for what ionizing radiation is. Ionizing radiation is actually composed of 4 different types of particle. You can think of it. Alpha particles, which is the helium nuclei, beta particles, which are electrons, gamma, which is radiation, and of course neutrons, which is one of the components of the nuclei, a non-charged subatomic particle. Now you notice that for each particle is a different weighting, and the different weightings depending on the amount of damage that type of particle can induce in terms of within the human body tissue. And the universal measure of radiation exposure is actually called the sievert. Now, 1 sievert is a terribly large number. So when we talk about radiation, we often talk about it in terms of microsievert, which is 1/1,000,000th of a sievert. And here are some fairly everyday examples of what ionizing radiation is like. I mean, for us walking around in a room or outside in the environment, we're probably exposed to about 0.3 microsieverts per hour. And over a course of an entire year, the background radiation is about 3,500 microsieverts. If, say, we were to get on a plane and fly for about 7.5 hours, because there's less radiation shielding flying high up in the air, we'd be getting, say, about 40 microsieverts in that 7.5-hour flight. And if we were to say want to having a CT scan, a big dose of X-ray radiation, you would get about 7,000 microsieverts in one hit. Now, these numbers sound rather large, but in fact, the human body is very, very resistant to ionizing radiation, and we actually need to be exposed to about 100,000 microsieverts over a year for there to be any increased chances of developing cancer. And of course, a much larger number of about 4 million microsieverts, or 4 sieverts, is required before we're looking at a fatal dose. So with that, I'd just like everyone to have a think about ionizing radiation and get a feel for it. It's not something that most people come across every day, because it's not like we're walking around with Geiger counters or dosimeters, but in fact, we are receiving a natural dose of radiation in every second of our lives. So today's lecture is here's a bit of an outline. We're looking at current power reactors. I'd like to show you about some trends in nuclear power. And also, I'd like to show you guys, what would nuclear look like if Australia were to have nuclear power. From there, I will say something about small modular reactors, and then I'll go on talking a little bit about advanced reactors. So current reactors, why are we interested in nuclear power? There's a lot of thinking and a lot of feeling to reduce carbon emissions. And amazingly, nuclear power does that just the best, hands down. If you look at, say, France, they are 75% nuclear power. And the reason why they have that wasn't actually to reduce CO2 emissions initially. It was just to have energy security. Why a lot of countries around the world look at nuclear power is because it's clean. It is actually the safest form of power across all types of different powers available. It is affordable. And also it could be responsible for supplying a lot of the baseload power around the world. The backbone of the nuclear fleet is centered on the pressurized water reactors. So for the global fleet of about 450 power reactors, 288 of them are pressurized water reactors. And some might like to call these things a glorified kettle, because what it is you're boiling water in a very, very large reactor pressure vessel. That 300-degree water, the heat of that is transferred to a heat exchanger where it generates steam that turns a turbine. And schematically, it's really just that simple. You have a core, you have a pressurizer to maintain about 150 atmospheres of pressure, and that heat is delivered to your heat exchanger, and it just gets cycled back through a pump. Where did it all come from? Well, the Americans actually invested a lot of time and effort into creating the first pressurized water reactors to power their submarines. And from there on, the thinking was, well, let's see what happens if we put one of these pressurized water reactors on land. And they demonstrated that back in 1958 with the Shippingport test reactor. From there, this here is the schematic of what a pressurized water reactor is. There's a little bit of a story of how I came to be very interested in pressurized water reactors. I actually was interested in working at ANSTO more because it was a fairly high-tech place, and I like doing engineering, doing it well. And initially, I actually wanted to get into fusion, and I thought, well, this is rather complicated. I thought maybe there's a more elegant and simpler way of generating power. I looked at some advanced reactor designs, meaning sodium fast reactors, molten salt reactors, and eventually I kind of came full circle and looked at light water, pressurized water reactors. And the reason why these pieces of kit are so interesting is just the way it generates power so elegantly and efficiently. You can see here, the coolant is light water, just very, very clean, say, tap water. The moderator, which is a material that slows down the neutrons so that can be more easily absorbed by the uranium fuel, is also light water because it has a high hydrogen content. And also the neutron shielding is somewhat done by the light water as well. And so with one material actually satisfy three different things that a reactor needs. The materials used in a pressurized water reactor is also very well known. Uranium dioxide, a ceramic that melts at a very, very high temperature above 2000 degrees. Fuel pins are made from zirconium alloyed with, say, 2% tin. And neutron absorbing control rods, which kills the nuclear reaction, can be done with silver or boron carbide. And the vessel just made of stainless steel and high tensile steel. So the operational characteristics of these reactors, they operate about 300 degrees. And it's pressurized to about 150 atmospheres. So for those people out there not engineer or scientifically trained, it's 150 times the pressure of what we're experiencing right now in this room. So the steam turbine efficiency is about 33%. And the fuel burn-up ratio is about 60 gigawatt days per ton of heavy metal. So what that means, it means it could provide a gigawatt for a complete day. That's what gigawatt days mean. So 60 gigawatt days per ton of the uranium. And the operational life of these pressurized water reactors is 60 years. So this is what actually uranium dioxide pellet looks like. This particular fuel assembly is actually Russian, for Russian VVER. And you can see it's only very, very lightly radioactive when they're actually putting these fuel pins together. And during refueling, so what happens with these reactors is that they're refueled every 6 months or so, and the fuel gets taken out about every 18 months. What happens is that they flood the space above the reactor pressure vessel, they fill it with water, because I mentioned that the water is actually a neutron shield and radiation shield. And here you see one of the fuel bundles being lifted out of the core. So once the usefulness of these fuel bundles is exhausted, they spend about 10 years in the spent fuel pool, because what happens is that after these fuel bundles have been irradiated, they give off decay heat, and that decay heat has to be removed. So what they do that, and to do it most efficiently, is just to have them just warmly heating a pool for about 10 years, after which they're taken out and put into a dry cast. And then from there on, they could either reprocess the fuel, as the UK and France does, or they could be put in the waste repository. Now, one of the most important things to note is that for used fuel or spent fuel, when we put them in the repository, people shouldn't really call it a dump, because really these repositories are engineered, understood engineering solutions. I really dislike using the word dump, because it just means uncontrolled and messy, which a waste repository is not. So looking at some of the other reactors around the world, as I mentioned, 288 pressurized water reactors. The others are boiling water reactor, which is basically a pressurized water reactor, but with one single loop where you actually create the steam inside the primary loop itself. The other designs are really legacy designs from different countries at the advent of the nuclear age. So for example, in the UK, they still have 14 gas-cooled reactors going. And in Canada, which is home of the CANDU reactor, they have the CANDU pressurized heavy water reactor, which uses heavy water to slow down the neutrons in order to create that fission process. Still in Russia, there are a couple of RBMKs operating. So these are graphite moderated water-cooled reactors. And of course, there are also 2 operating sodium fast reactors in Russia as well. So nuclear power trends. Here are just some stats of the amount of installed capacity of nuclear power around the world. You can see the US is leading still with about 99 reactors generating 100 gigawatts. But notice also the upcomers. So up and coming is China, South Korea, a lot of the Asian countries that only have a small percentage of their current electricity generated by nuclear power. Most of the new builds are actually in the East Asia region. So if you look at the history of Nuke-plant constructions year by year, here's a nice graph I found. It shows that there were a very, very large amount of reactors under construction at any one time. And it hit a high watermark when we had, I think, what would be deemed as the first major nuclear accident over at 3 Mile Island, where you had a partial meltdown of the core. And then it has fallen past the point of where you had Chernobyl, and it kind of flatlined. In about midway through the 2000s, we had somewhat of a nuclear renaissance. And of course, that was held in check by, unfortunately, the Fukushima accident. But what's important to note as well is that through each accident, there are more lessons learned. And as a result of that, nuclear safety has improved. And still, nuclear power and pressurized water reactor is a mainstay and a main supplier of electricity around the world. So currently, if you look at the constructions around the world, I think this number is a little bit dated. I think China has about 19 reactors currently under construction, but it's closely followed by India. I think these, the pressurized heavy water reactors under construction, after the first AP1000 was switched on in China, only in July this year, the Indians signed off for another 6 AP1000s to be constructed, and Russia as well, having more construction, South Korea, and then you've got a lot of other countries that are dipping their toes in nuclear power builds with like 1 or 2 designs. So a good example of a successful nuclear build would be the UAE in South Korea. The UAE built from nothing. About 10 years ago, that was when they first thought about nuclear power. They looked around the world, they said, okay, who has the most robust supply chain? They identified South Korea and they partnered with them to build 4 1.4 gigawatt reactors at about $25 billion, which normalizes to about 4.4 million per megawatt of capacity. So I would say this number here is probably the most successful the most economic and successful nuclear build we have currently. But in fact, China is also doing better, but probably a lot better, because China has their own indigenous design, as well as being able to call upon local finances at 3% discount rates, which brings that number down even further. So recent success stories in China includes the 2 successful new builds of Western design. This is very important because these designs would be regarded as Gen 3, would be regarded as superior in safety, and they have now been proven. They've been switched on conveniently at the turn of the financial year. And from there, the Chinese could make a decision to build out a whole lot more. And also, it paves the way for these reactor designs to be built elsewhere as well. So what's interesting, though, is that if we make a comparison of the same design being built in the East and the West, you can see here that builds in the West are more than double what it costs in China. And partly that's to do with cheaper labor, partly it's to do with China having a more robust supply chain. But in the end, it somewhat highlights that in the West, there hasn't been a lot of builds in the last 30 years, which is why there has been delays, and there has been a little bit of a need to prime and restart the nuclear build market there. So I'd just like to also talk about what's happening in the very near future in China. China is commissioning their first full-scale high-temperature gas reactor. Now, these reactors are interesting because they'll be implemented and deployed inland using air cooling. And this will be a bit of a game changer for them, because basically all their pressurized water reactors are along the seacoast using seawater for cooling. But as you know, and as the Chinese definitely know, is that there's a large pollution problem. So when they think about nuclear, actually they think about it from a point of view of clean air and clean energy first. And so by being able to implement these designs inland, they can actually realize that dream of having both industry and clean air at the same time. So the cool thing about these designs uses helium as the coolant. Why use helium? Well, helium's 10 times more thermally conductive than air. To slow down the neutrons so that can be more easily captured by the uranium fuel and split and create fission processes, they use graphite instead of water. For the neutron shielding, it's concrete. They use also a very interesting fuel design. So instead of the rods that I showed you earlier, they use these little carbon balls, which are what they call pebble bed fuel. And inside these pebble fuel are thousands upon thousands of little 0.5 millimeter diameter uranium dioxide pellets. And the interesting thing about this fuel design is that it's highly accident tolerant, so that what you can have is you can, if you want to switch off the reactor, you can switch it off. Say you've got a pump failure. Doesn't matter, because what happens is that the decay heat is simply removed by natural convection from the air itself, and also the trisol fuel is resistant to the release of any kind of fission gases up to 1600 degrees C. So these are the kind of numbers that's very interesting. Operational characteristics of this reactor, as you can see, it's very high temperature, 750 degrees. It is therefore able to turn a supercritical steam turbine at 40% efficiency instead of 33%. And also the interesting thing is the Chinese have thought ahead. So what they have is that they've got these reactor modules, each one of them outputting about 105 megawatts. But their plan is actually to put 6 of these modules feeding one turbine itself. And those turbines actually have already been built because currently they're being powered by coal power. So what they want to do is basically substitute the coal-fired power plant with the nuclear units. Okay, so let's have a look at Australia's energy future. How would nuclear look like on the national energy market? New South Wales is facing some challenges ahead. Starting 10 years from now, we're going to see the first of a lot of coal-fired power plants coming offline towards the end of life. And the question, of course, is what will replace these generation units? Now, of course, a lot of people like the idea of green and they like the idea of low emissions. What is very important to note, though, is that as nice as renewables are, as nice as wind and solar are, they're not on all the time. And so what that means is that every time you build a wind turbine or a solar power plant, 60% of the time, it's actually backed up by gas. And gas, of course, isn't carbon neutral. So when you look at South Australia, for instance, at some of the time when the wind dies down, gas takes over. And you're going to be looking at, it could be that if we replace all the coal-fired power stations in New South Wales, Queensland, and Victoria, you could have lots and lots of gas burning. So the question is, like, maybe there's something else that could satisfy that shortfall in power. But as I was looking into this question, I actually came by the work of Dr. Robert Barr, who's the president of the Electrical Energy Society of Australia. And he had a very interesting model. So what he did was to look at the AEMO data, the Australian Electricity Market Operator data, get the complete demand on the eastern seaboard for 5 states, and also grab their data for the amount of solar and wind available in those time periods. And he plotted everything out for 21 days in January last year. So what you're seeing here is actually the demand curve that cycles throughout the day, and then also displayed in bands of color representing different types of generation is how that demand is being satisfied. So you can see here, as you can see, oops, okay. So the brown layer is brown coal, the cheapest form of power possible. The black represents the black coal. And then the variation is satisfied by a combination of closed cycle gas turbine, hydro, open cycle gas turbine, and green, which is the wind power. But of special note is just, you can look at this and you can see just how structured the current national electricity market is. And this is the whole reason why we can still expect somewhat reasonable power prices. At wholesale is about $30 per megawatt hour average over a year. But the question is, what would that look like in the future? So I just want to run through a little bit more into Robert Barr's model. So as I mentioned, the NEM load is from the AEMO data. What his model, how you run the model is that you can actually select different amounts of generation sources. And what the algorithm does, it picks those options which are cheapest first and dispatches them. But of course, even better than being the cheapest is if you're either wind or gas, because currently the AEMO market allows wind and solar to have priority on dispatch on the grid. They must be dispatched because there's no viable industrial scale storage. So from the other assumptions are that for this model, there's no transmission constraints. Base loads are always operating 100% efficiency, which is not really the case. And But the extra transmission costs from bringing in all that power from the diffuse sources of wind farms and solar has been incorporated in the price, in the cost model. And Dr. Robert Barr has also assumed a discount rate of 6% per annum for calculating the levelized cost of electricity. So say if we really want to seriously reduce CO2 emissions, we could possibly replace all the base load with nuclear. What's interesting is that if we take the figures from South Korean builds, you know, what I showed you earlier, the build of the price, the levelized cost of electricity is actually not that high. It's only about $90 per megawatt hour, which is just slightly more than the $68 a megawatt per hour I was showing you earlier. Now, when I say that, actually, that's the price for replacing everything we've got currently with exactly the same thing. It's not just the price of what we're paying now, which is about $30. But a very, very interesting display is this graph, which is what Dr. Robert's bar calculation is for AEMO's projection into the future, with a lot of solar on the grid. It's a little bit complicated, but I will seek to explain. You can see the sharp spikes, which protrudes above the demand curve. That is an excess amount of solar that is going into pump storage, charging up pump storage, pushing water up a hill, and that is discharged at the latter half of the day in that light gray you see. So every day it cycles from pumping water up a hill and then discharging, pumping water up a hill, discharging. That's all very well and good. The problem, though, is that you can see that those large amounts of solar coming online towards noon, it actually penetrates right through the market, and you have a shutdown, essentially, of your baseload system, which is black coal and brown coal. Now, the thing is, those coal-fired generators, they're not designed to operate like that. You're going to have a lot of strain on your system, and most possibly, you'll never even see this scenario in real life because those coal-fired power generators will be completely out of the market way before this happens. Now, finally, the graph, this shows a plot of the levelized cost of electricity compared to the emissions intensity per megawatt hour. You can see just how superior nuclear can be in terms of both cost and emissions, which is right down on the bottom left-hand corner. Currently, we're at number one, which is the base case existing NEM approximation, about, say, 800 grams per kilowatt hour. And the question is, where do we want to travel along this graph? Do we want to, say, go to AEMO's approximation of about $240 per megawatt hour, or maybe something in between? This is the whole reason why I think nuclear ought to be in the conversation. Finally, I think that the largest impediment to the possibility of nuclear power being introduced is actually public opinion, because unfortunately, no one really knows about radiation, and people somewhat gets apprehensive when we think about nuclear power. But what's really interesting was that there was a survey done in ANU, and it was found that more people were against gas fracking than they were actually against nuclear power. What's also interesting as well is that I think there's a large majority in the center which don't know a lot about nuclear power, but I think there's room to show them this information and then get them to have a rethink about what nuclear can possibly do for Australia. Okay, so let's move on to small modular reactors. These are near future technologies. I would like to say that. Small modular reactors, near future designs are basically been miniaturized PWRs, miniaturized pressurized water reactors of 300 megawatts or lower. So why are we considering these? Well, if you look at history, reactor sizes have only gotten larger. And the reason for that is because for every site, you're going to have an X amount of costs for safety systems, licensing, security, and they want to maximize the amount of output, which is why we had gotten larger and larger reactors. The only problem, though, is that these reactors have become so large that just one reactor might cost you about $6 to 10 billion US dollars. And so, you know, it's hard to imagine a utility in Australia betting a farm on one of these reactors. So what the Americans have done in particular is to innovate, and to innovate by making these reactors compact and modular so that they could be created or fabricated much quicker, say 3 years instead of 7 on site. You can imagine these reactors as being things that come out of a factory on an assembly line, similar to, say, commercial passenger airplanes. The idea of this is that you could manufacture in the factory, you can transport them out, establish them on a site, on a much quicker turnaround than you would be able to for gigawatt reactors. So for a particular type of reactor called the NuScale, you are looking at about the same cost per megawatt as the large South Korean reactors. But the most important thing to note is that these modules are much cheaper compared to a large reactor. So what that means, financially speaking, is that your negative cash flow is not anywhere near as bad, and this would make the financial case work. Another interesting characteristic of these designs is that you've got a smaller core. So we're looking about, say, only about 10% of the amount of fuel compared to a large AP1000. And this also improves and helps with our safety case, because if you've got a smaller source term, it makes for the removal of the decay heat, which is about 1% of nominal power, much easier. And so in the case of NuScale, where they have a large water reservoir, you can shut the reactor down, and that large water reservoir, which is equivalent to 80 Olympic-sized pools, would be able to take all that heat away, all that decay heat away from the fission products, take it all away, and you don't actually have to have any operating intervention at all. So in the nuclear engineering terminology, this is what you would regard as being inherently safe as well as passively safe. Now, due to this fact that it's passively safe, you could also make the case of the regulator to shrink what they call the emergency planning zone right to the site boundary. And in fact, the NRC, the Nuclear Regulatory Commission, has given that the nod of approval already. So it could be that you would be able to use these small modular reactors to retrofit current coal-fired power plants so that they could, basically you'd be able to have them replacing those coal-fired power plants without having to replace the grid or to do grid build-outs. And given that they're smaller in output as well, they're much easier to site than large reactors. So this here is just a schematic of the New South Wales electricity grid, and you could see there are only a few points for large power reactors, whilst many points for small modular reactors. Time frame for deployment. There's currently 5 designs with an 8-year time frame of deployment. You've got NuScale, the American design, Karam, which is Argentinian. There's been a bit of news lately about the Russians commissioning their floating power reactors to 35 megawatt units, which is being towed to the Arctic Circle to power a little Arctic city. The Chinese have the ACP100, and the South Koreans also have the Smart Reactor. So that brings us to the close of the small modular reactors or pressurized water reactor variety. Looking into the future, though, are advanced reactors. And what I mean by that are exotic coolants for these advanced reactors: sodium, lead, gas, molten salt reactors. This is a very, very famous slide of the Gen 4 designs. Although I would give my own slant on it, I would say that I would see the top 3, as well as the lead-cooled fast reactors, as being fairly viable solutions. I would say that the supercritical water reactor and the gas-cooled fast reactor as being less likely to come on the market soon, because less work has been done on it, and also the safety case is much more challenging. For Australia, we've recently joined the Gen 4 Forum, and Australia will be focusing on the high-temperature gas reactors as well as the molten salt reactor. So when I say advanced reactors, inevitably, a lot of these designs are what they call fast neutron reactors. And to explain that, I just want to show this graph here, which shows the cross-section, capture cross-section of various fuels or uranium, plutonium fuels at different neutron energies in mega electron volts. So when we talk about a thermal spectrum reactor, such as a pressurized water reactor, what that really means is that you've got a neutron and you slow that down to the kind of energies you would find, say, air particles or very hot water, that kind of slower velocities. Whereas when neutrons are created in the fission process, they initially are very, very fast at moving about, say, 4% of speed of light. And for a fast reactor, what you want to do is not to slow those neutrons down, but to utilize them to burn your fuel, to breed more fuel, or to burn actinide waste. And so this is what we're talking about in terms of fast and thermal neutrons. What's interesting as well is that you could see that the capture cross-section is much higher at thermal spectrum, so about 3 orders of magnitude. And what this means is that you actually don't have to cram as much fuel into a volume space in your reactor core. And so this is also a reason why there hasn't been that many fast reactors created, because basically it means you have to have a more compact design that necessitates a superior coolant, such as sodium, liquid sodium, which is a metal, or molten salt, which is which has a high temperature operating range, but also brings about it more challenges with your corrosion. So your sodium fast reactor, I'm just going to go through this fairly quickly, because this in itself is another topic. The two operating designs are the BN800 and BN600 in Russia. Two sodium loops, one water loop to take the heat away. And the story of this, actually, is a good news story, is that the Russians have used the BN600 to burn weapons-grade plutonium for a long time. For those of you that's into detail, you can see that, in fact, in the fast spectrum, you can go back one slide. In the fast spectrum, the plutonium fuel has a higher cross-section than uranium itself. So it means that fast neutron reactors are actually plut burners, not so much uranium burners. And I'd also like to touch on the molten salt reactor, which was a development in the US. Initially, the US wanted to power a strategic bomber by having a very compact reactor core. And so they selected a very, very good coolant, a very, very efficient coolant, but in the form of molten salt. Of course, it was kind of crazy, and I think Alvin Weinberg was the director of ORNL at that time, said that it was a crazy idea, but we didn't turn down the funding. And the interesting thing about that is that after that project was canned, it was revived in the form of the molten salt reactor experiment, where they directly dissolve the uranium tetrachloride crystals, the fuel, into the primary coolant itself. So this reactor actually doesn't have any fuel rods or fuel elements. The interesting thing about this design, again, the moderator used was graphite. The coolant uses something called FLIBE salt, which is lithium beryllium fluoride. Notice that those elements are rather low in atomic number, and that's to also moderate the neutrons. The materials, well, they use rather exotic materials such as nickel, and neutron reflector was also graphite. Interestingly, though, is that the operating temperature was 600 degrees, very high. So in theory, you can drive a Brayton cycle or gas turbine at a very high efficiency of 45%. But because the salt only boils at about 2,000 plus degrees, you don't actually have to pressurize the design at all. So it's just almost like a cauldron of super hot molten salt in which just carrying a primary coolant. The interesting thing, though, is that this project was shut down in 1969. It's been dormant till now, because what's really interesting is that both the Chinese, the Americans, and Europeans are now getting back into molten salt reactor development. TerraPower, which is the company of Bill Gates, is looking at a molten chloride fast reactor to burn spent fuel in the US. And the Canadians, by the name of Terrestrial Energy, is also looking at an integral molten salt reactor design. And that's not to mention the other major projects, such as China's SINAP, $3.3 billion molten salt reactor program, Elysium, Moltex from the UK, Transatomic at MIT, Kairos over at Berkeley. So there's a lot of activity going on with the research of these reactors. However, I would say that there are different, they're a race with different competitors with different amount of resources. And so you might see some designs come in the near future, such as the integral molten salt reactor and the other designs, which are probably a little bit further off. Finally, I'd just like to touch on some other developments that's very interesting. As you know, there's been great leaps and bounds being made in space exploration. And of course, if you go anywhere, say to Mars or beyond, it doesn't make any sense to put solar panels there anymore, because you just basically don't get enough energy. So the NASA people working with Los Alamos has designed a space-worthy reactor in a very, very compact, robust form. And this design has already been tested, and it will be flying in the near future. So looking at this design, it's very, very unique. It's got a metallic core of an annular billet of highly enriched uranium. The design is slated for 10 years, operating at 1 kilowatt electric constant. To reflect the neutron back in the core for neutron economy, they use beryllium oxide reflector. The central control rod, as shown in yellow, boron carbide, is extracted only to start the reactor. This is really interesting and very different from most reactors, because most reactors, you vary the control rod position in order to vary your reactor power. In this design, what they've got is that they've got 8 they've got 8 sodium heat pipes running on the exterior, and the power of the reactor is actually regulated by how much energy you're taking away from the core. So if say you've got a complete failure of your Stirling converters, the piston kind of engines at the top, what will happen is that the core of the reactor will get hotter, it will expand, more neutrons will leak out, but it won't melt, because what happens is that as the core expands, there's less fuel per volume, and so therefore overall power goes down. So it will remain very hot. And so I think, for those interested out there, should just Google the kilowatt reactor design and just do a little bit more research. I think I've kind of exhausted everyone. I've exhausted my allocated time. So I'd just like to thank everyone, and I'll take questions.
Thanks very much, Mark, for a wonderful talk. We've all learned a lot. We do, in fact, have a bunch of questions from the online watchers, but I'd like to open the floor to any questions if anyone has any. Okay. Well, from one of our viewers, they ask, the recent financial situations in Areva and Westinghouse were reported in the media to have arisen from nuclear construction projects. Now, do you have any comments to say about why that might happen?
Well, yeah, I think I might have somewhat covered that in my comments during the presentation. Well, first of all, both Areva and Westinghouse are Western builders. And so for the Areva EPR, European Pressurized Water Reactor, their first build was in Olkiluoto over in Scandinavia. And part of the reason for such a large delay was because they had the Fukushima incident. And as a result of that, the local regulator stopped the work, and then they had to review. So a point that comes out of this is that when you do a nuclear build, you want to be very sure that your design is very, very well thought out and okayed by the regulator before you press go. Otherwise, you'll be losing a lot of money paying that interest rate for when you're just building the reactor. So that's the first point. And the second point is that if, say, for anyone wanting to build nuclear power, what they also want to do is that they want to partner with a builder that's had lots of experience with a continuous build kind of schedule. So I would say the South Koreans have been very successful, as well as the Chinese. But I also think that the Americans are very capable. The question, of course, is whether they can demonstrate it and prove it when they say build the first of a kind NuScale reactor. To open on that, NuScale, as I mentioned, 60 megawatts per module. But the thing is, they usually implement them in the plant of 12 units, outputting 720 megawatts. Now, the thing is, if you set up a production line and you say, create, you fabricate 12 units, actually, you're already halfway down the cost curve and beyond, and you have demonstrated that you have your supply chain thought out. So I think getting back to the main question, comments on Westinghouse and Areva, it's been a learning exercise. They have successes, as I mentioned, in China, but now the challenge is to bring those units online elsewhere in Europe and the 2 AP1000 builds over in Georgia.
Fantastic. Well, I have a question. I was wondering about the Chinese context. Have we seen any slowdown in their builds or their approval of new builds in a similar sort of way that we've seen kind of the slowdown in the nuclear industry more generally in the West?
I actually have a really good graph to show the almost exponential increase in the amount of nuclear electricity the Chinese are bringing onto the grid. So getting back to thinking back to some of the slides before, China's about 4th or 5th in terms of the sheer amount of terawatt hours generated from nuclear sources or capacity, but that's not to say the Chinese haven't been very thoughtful and circumspect with the safety of their nuclear builds, because the amount of new builds approvals had actually stopped after Fukushima because everyone was doing safety reviews. But having reviewed it, then they said, okay, we're just going to go with the EPR and also the AP1000 builds. And now that they've been brought online and have been demonstrated to be successful, then they would consider building a whole lot more of them. Some of the other indicators that the Chinese are thinking very seriously and look upon nuclear positively is that they're also, I think, the CNNC, Chinese National Nuclear Corporation, is establishing a nuclear engineering school, a dedicated nuclear engineering school, just to train all their technicians, which will man their PWRs.
Just on those safety reviews that were performed as a post-Fukushima exercise, did anything come out of that with respect to modifications or changes to those Gen 3 reactors?
The thing is, with, say, the example being the Americans, they had a Blue Ribbon Commission, and there are a lot of very good information that came out of those reports. So, for instance, in the US in particular, they've set up these quick response sites where, say, if there were to be a tsunami or a station blackout, then those ready crews would be able to have flown in at short notice to reconnect the power, and in order to be able to make sure that there's a sufficient coolant in those reactors to take away that decay heat, and also the manner in which operator behavior and reactor manager behavior is very important. Part of the reason, unfortunately, in Fukushima for that accident to unfold like it did was because there was a delay in the decision making, and so there were a lot of reviews as to how to streamline the administration process and to make sure the reactor manager has a lot of power to make sure that the reactor is brought to a safe state without delay. I think those are very important lessons.
Hi, Mark. Thanks for your talk. I have a quick question. You mentioned an interest in fusion. Are we any closer to having fusion as a viable energy option?
Yeah, look, we are definitely closer, and there's a terrific amount of work being done on the ITER project. So every step and every discovery and every new experiment brings us closer to that realization. The reason why I seem to be a little bit more downtrodden on fusion, is if you look at the tokamak design, which is pretty much the focus of a lot of the international effort, it is a terrifically difficult physics problem. Because as you probably know, you might have a little volume space here of energetic plasma, which is charged, and that sees all the different volumes of charged particles whizzing around. And of course, these volumes of charged particles, they're going to repel one another, etc. And so you actually have a set up a fluid which is inherently undamped. So therefore, there's really no one numerical tool analysis that would definitely tell you the exact behavior of these tokamaks until you actually build them and test them. And so this is the reason why, I guess from my own point of view, I'm trained as a mechanical engineer, so I would prefer to solve the problem rather to select the most optimal solution before solving the problem.
We actually have a couple of viewers from the Australian team to ITER, so a few comments on fusion, I think, welcome those viewers. I have one more question from another watcher online, though, in regards to those advanced reactor designs that you talked about. The question is, I suppose, how close are we to seeing some of those designs come to kind of licensing, companies or countries seeking licensing? And with respect to Australia, what are the obstacles to realizing those more advanced designs?
I think so. For instance, with sodium fast reactors, it's already been realized in Russia. What's interesting is that even with the fall of communism, it really didn't slow them down. I could say that. With advanced reactors, I know that, so for instance, with the integral molten salt reactor that's currently under research underway in Canada, they actually have a very aggressive timeline. So I'm hearing that they would want to be building something by 2026. Now, of course, these aren't the kind of reactors that we have all around the world, PWRs, with a 60-year time frame. So they're talking about something like 7-year time frame before they have to swap everything out, because they're not quite, no one quite knows how the corrosion will play out. So this is somewhat the catch-22. If you want to build a reactor, you want to have ASME certified kind of materials, things which they've tested. And because most of the operational experience has been surrounding pressurized water reactors, that's what they know how to license. So in some ways, I think it's a bit of a chicken and egg, and basically someone actually just has to build something first. And I think maybe for Australia's sake, it's probably a safer bet to look at pressurized water reactors, maybe in a small modular reactor variety, before we see a first of a kind, say, molten salt reactor being implemented here. Because especially with nuclear build, what you really want is not to necessarily be the first movers. You'd really want someone to build a first of a kind, because ultimately first of a kind is a kind of an experiment, and it's going to take a little bit of time to get right. And so, yeah. But I would say that Australia should be wise to keep a tab on all the developments so that we know how to capitalize on the successes overseas.
All right, thanks very much.
Thank you.
I think that's it for questions from the floor and from online. So I'd like to once again thank you very much for speaking to us today. Thanks to everyone for coming along. I hope very much to run, or for AusYGN to be able to run more of these in the future. So keep your space. And thank you very much again. Show a round of applause for Mark, and we'll cut it there.